First, we know that we have a frame rate of 30 FPS. We can use the global variable frame rate, which returns the number of frames in 1 second. And we'll also have to divide our speed vector by the ticks per frame global variable, which contains the number of ticks in 1 frame. At 30 FPS, the number of ticks is 160. A tick is the smallest time unit in 3ds Max. There are 4,800 ticks in 1 second. Obviously, when working at 30 FPS, 1 frame contains 4,800 divided by 30, or 160. When working with PAL, the European Standard frame rate, we're getting 192. And when working for movies at 24 FPS, we're getting 200 ticks per frame. This means that the number of ticks per second is a constant of 4,800, and the number of ticks per frame changes depending on the frame rate. Now that we have divided our speed vector by the number of frames in a second and then by the number of ticks in 1 frame, our speed is correctly expressed as units per tick. If we would close the script and disable the speed operator, the particles will still move exactly as before at 1 unit per frame, which means that our script recreated the same behavior as the speed operator. If we would disable the script and enable the speed operator, we should get exactly the same result. Now let's go a step further and see how we can keep the magnitude of the speed assigned by the speed operator, but change the direction of the speed using the script operator. We'll change our code to first read the original speed of the particle from the particle speed property. Then we'll calculate a new speed as a normalized vector taken as a random value between the vectors minus 0.5, minus 0.5, minus 1, and the vector plus 0.5, plus 0.5 minus 1. This means that first a random vector is going to be calculated by the random expression, and then the result is going to be turned into a unit vector, which describes a direction but has a magnitude, that means a length, of exactly 1 unit. At this point, we can assign the new speed to the particle speed, but multiply our unit vector with the length of the original old speed. This means that the length of the vector assigned by the speed operator is going to be preserved, and only the direction defined by the unit vector that we calculated randomly is going to be changed. Let's close our script and take a look at the result. Now the particles will move in random directions along the minus z-axis, but still at the same speed of 1 unit per frame. Let's add a cache so we can scrub back and forth. And take a look at the result. If we would change the speed in the speed operator, our particles are going to use the same speed and only change the direction based on the script operator. Since we're using a random operation, it is a good idea to make sure that whenever we initialize our script operator, the random seed is set to the same value. This way, if we would send our particle system for rendering to multiple machines, for example on a network of rendering slaves, the result would be consistent. As you can see, when we change the speed now, the vectors keep their original direction calculated once by the script operator. If we would remove the seed method from the init handler, changing the particle flow in any way recalculates new directions which are not consistent. This example shows again how useful the normalize function is and how a unit vector can be used to define a direction in space and then be multiplied by a magnitude or by a scalar value defining the length of the vector.